Hi everybody and welcome back to Mr. Carroll's Classroom. Today we're going to cover the properties of logarithms. So let's check them out. Okay, so in order to come up with the properties of logarithms, we're actually going to create a corresponding pair for every property of exponentials. So let's go ahead and start. So we're going to start with the product rule. So the product rule for exponentials says if I have b to the whatever base for this exponential to the power of m times b to the power of n, then that's equivalent to b times m plus n. And if you're looking for proofs of all of these exponentials, by the way, which there are actually more properties for exponentials, then go back to my previous lesson with properties of exponentials, and we cover all of those with the proofs. But anyways, what is the corresponding product rule for logarithms? Well, we have log base b of, and here's the key here, if I have two things that are multiplied inside of these parentheses, in this case m times n, then I can split those up with addition here. That is equivalent to log base b of m plus log base b of n. Okay, so let's go to the next one here. We have the quotient rule, and for an exponential, that looks like if b to the power of m divided by b to the power of n. Oh, and by the way, as I'm talking about these, it is important that all of these have the same base. Otherwise, you can't apply the rule. But anyways, if I have b to the power of m over b to the power of n, then that's equivalent to b to the power of m minus n. So what is our corresponding logarithmic property? Well, here it is. If I have log base b of, and again, inside of here, if I have m divided by n, then I can again split these up with subtraction. So that is equivalent to log base b of m minus log base b of n. So the numerator minus the denominator. All right, and then we have our power rule for exponents, which says that if I have b to the power of m all to the power of n, then that's equivalent to multiplying m times n here, which is b to the power of mn. And so the equivalent logarithmic rule here, or the logarithm power rule, is if I have log base b of m to the power of n, and actually it's really important here to understand that it doesn't actually matter if n is inside or outside of these parentheses, just so you are aware, it is the same. But anyway, if I have log base b of m to the power of n, then I can move that n out front, which is actually a very powerful rule. It's how we typically get exponents, or variables, I should say, out of exponents, so and into the to the main term here. So anyways, you can move that n out front, and so that is equivalent to n times log base b of m. Okay, so now there is one more really important rule for logarithms, but it doesn't really pair with an exponential rule. It really kind of comes from the power rule, and so that's called the change of base rule. And so in this case, and we're not actually going to see any examples today, but we will in future lessons. But if I have log base b of m, then I can actually rewrite this as log of m divided by log of b of any base. In this case, I'm using base c, but this c could literally be anything. So let me just repeat that. Log base b of m is equivalent to log base anything of m divided by log of that same base of b. Now this actually can be, and you can prove this, but this can be really important because on calculators, typically we only have the common base, which is base 10, and the natural base, which is base e. So what happens when you want to solve some kind of logarithm with any other base? Well, you would actually have to use the change of base formula here, so or rule. Now that's not true of all calculators. Some calculators you can put in any base, but many of them you cannot. Okay. All right. Now, all of these are our basic properties here of logarithms. All of these can be proven using exponentials because that's how they were created. Remember, a logarithm is simply the inverse operation of an exponential, right? So they should be related in some way. So now you can prove all of these on your own, but I am going to offer one quick proof, and we're just going to do this first one, and you're going to kind of see how it works. And I would actually encourage you after this to go ahead and see if you can use the same type of method to prove maybe the quotient or the power rule. So anyways, so let's go ahead and prove this product rule. So if I let x equal log base b of m and y equal log base b of n, then let's go ahead and we're gonna convert these logarithms into exponentials. So if x is equal to log base b of m, then it's the same thing as saying b to the x is equal to m. And same here, right? If y is equal to log base b of m, then we can say we convert this logarithm to an exponential equation, then that's b to the y is equal to n. All right, let's continue. Now, since we're trying to prove the product rule where we're multiplying these two together, we're going to multiply m times n. So m times n is b to the x for m times b to the y for the n. Now, let's simplify this here. So b to the x times b to the y is b to the x plus y. And now what I'm going to do is I'm going to take the log base b of both sides of this equation. Why am I going to do that? Well, because this exponential over here has an exponential of base b. So a log base b of an exponential base b should cancel those out. And that's what we get here. So we end up with log base b of m times n on the left. And then over here, log base b of b to the x plus y. And again, you can think of this exponential is multiplying by the base over and over and over again, while the logarithm is dividing by the base over and over and over again. So those are going to cancel each other out and just give us this x plus y. So let's go ahead and show that. Okay, so here you can see that these two are canceling, the exponential base b and the logarithm base b. They're doing opposite operations, so they cancel. And now finally, what do we say to begin with? We actually said that x is equal to log base b of m and y is equal to log base b of n. So if I go ahead and substitute for these, let me kind of move out of the way, scrunch down a little bit here. What do I end up with? Well, we just proved, right, that that this product rule fits, right, by utilizing some of our exponential properties, essentially, okay? And also, by the way, the inverse. So we really just use exponentials, and we use this inverse operation of an exponent, which is the logarithm, okay? All right, so let's go ahead and continue. And what I want to do first here is just kind of, we just saw a big table of how all of these properties correspond. Don't get too confused. There aren't that many properties of logarithms. We have the product rule. We have the quotient rule where they're dividing. We have the power rule. And then we have the change of base formula or change of base rule as well. So these are really the four properties that we're going to utilize. And again, we're actually not even going to touch the change of base today. But anyways, let's continue. Okay, so I want to remind ourselves, like, what is, what is a logarithm, and just remind ourselves that it is the inverse of an exponential, right? So these two are equivalent statements. If I said y is equal to b to the power of x, that's base b as this exponent, power of x. I could convert this to the log base b of y is equivalent to x. These are equivalent statements. And how do we actually know that these are equivalent statements? Well, I'm actually going to offer you two proofs, one from the left-hand side, and then we're going to do it to the right-hand side. So let's start with the left and work our way to the right. So very quickly, if I have y is equal to b to the x, I'm just going to rewrite that down here with some room, because what I'm going to do is I'm going to take the log base b of both sides, and we know if we have an exponential of base b, where we're multiplying by b over and over and over again. If we have the log base b of that, where we're dividing by b over and over and over again, well, those two operations are canceling out. Multiplying repeatedly and dividing repeatedly by b, these are going to cancel each other out to get y. And when we do that, what do we end up with? Well, we end up with, on the left, log base b of y is equal to x, which is the right-hand side here, right? That's that equivalent statement. And then I'm going to go ahead and just to show you real quick, that, yeah, we can go from the right side and work our way to the left as well. So if I start with log base b of y is equal to x, then what's the opposite? Like, how am I going to get this y out of here, essentially? Well, I'm going to do the opposite of log base b, which is an exponential of base b. So what does that look like? Might feel a little weird doing this at first, but take a look here. So you're actually taking b to the power of, the left-hand side is equal to b to the power of the right-hand side. And now I have an exponential where I'm multiplying over and over again by base b to the power of this logarithm where I'm dividing by base b over and over again. So those are going to cancel out and just pop out this y here, getting us y on the left-hand side is equal to b to the power of x, which is equivalent to our original exponential. Okay, so just a little reminder there that a logarithm truly is the the inverse of an exponential, and these two on the left, these two statements on the left and right are equivalent statements. So let's continue on here. All right, I want to cover. So now we're going to get into actually doing some math with these properties, and I want to talk about trivial cases first. Okay, so just like with an exponential, we have this trivial case of anything to the power of 0 is equal to 1. Well, we have the same thing with a logarithm where we have log base b of 1 is always going to be equal to 0. It doesn't matter what the base is. And what is this actually asking? Remember, a logarithm says, how many times do I divide this number here by the base to get back to 1? And in this case, I'm already at 1, so I don't have to divide it at all, or 0 times, which is why it's equal to 0. And if we have, here's another trivial case here, if we have b to the power of 1, well, that's just simply equal to b, right? Very trivial. Well, we have an equivalent logarithm trivial case here. If I have log base b of b, then that's equal to 1. Again, what is this asking? How many times do I divide the argument here by the base to get back to 1? Well, b divided by b one time is going to get you back to 1, so this is equal to 1. All right, and then last one here, of course, super trivial, b to the n is equal to just b to the n, and what do we have that's equivalent? Well, here we have log base b of b to the n is equal to n, and again, I've already kind of shown this twice already, but if I have log base b, I'm repeatedly dividing by b. And up here, this exponential, b to the n, is repeatedly multiplying by b. And so those two operations are going to be canceling each other out, just getting n out of here. Okay? Okay, so now let's go ahead and do some examples. Okay, so I went ahead and so these are our properties. So these are what we're actually going to use. However, just to note down here, these are our trivial cases, just in case these pop up. If I ever have like a log base anything to the 1 power, I can actually evaluate that to 0, right? And each one of these can actually be evaluated, just in case. Okay, but we're mostly just going to be utilizing the properties. So our first problem here is going to be to condense this expression, this logarithmic expression. So I have c times log base b of a is minus y times log base b of d. So we're going to look over and check out our properties and see what we can do to kind of smash this in or condense it. First thing I notice, by the way, is as I'm looking at this, is there are two terms. Okay. Also, I notice that the bases of these logarithms are the same, which means that I can actually apply these properties. If these bases were different, both of these are base b, if they were different, then you cannot apply the properties to combine these. Okay? All right, so let's go ahead and continue here. So the first thing I'm going to do to condense this is what we typically do first, is we look for these multipliers out front. Because according to this power property, the power rule, if I have a number out front, then that's the same thing as having that number up as an exponent. So I can move each one of these constants out front into the exponential. So let's go ahead and do that. So this becomes log base b of a to the power of c, and I want to repeat here, it doesn't actually matter if c is inside or outside the parentheses, it is the same thing. Anyway, and then we have minus log base b of d to the power of y. This is moving up into the exponent as well. All right, now let's condense this a little bit further. I'm noticing that this is subtraction now. And so I can apply the quotient rule because if I have log base b of something minus log base b of something else, then I can condense that into a fraction inside of the parentheses. So I end up with log base b of a to the power of c, this first one, divided by d to the power of y. And that's it. That is the answer to this problem. We have taken this stretched out or expanded expression, and we have applied our properties and condensed it in as much as possible. Okay, let's do one more. We're going to condense. In this case, we're going to use real numbers here. The base is still just going to be a variable here, but we'll apply actual numbers in here. So we're going to condense 5 times log base b of 2 minus log base b of 4. And again, I am noticing that these do have the same base, so I am going to go ahead and try to compress these. But before I combine these two, I am going to take care of these constants out front and move them in as exponentials. So let's go ahead and do that. So the 5 goes up inside of here to 2 to the 5th power. And actually, 2 to the 5th power is, 2 times itself 5 times. So let's go ahead and evaluate that. That 2 to the 5th power ends up becoming 32. So right now I have log base b of 32 minus log base b of 4. And so now what I can do is I can apply the quotient rule and say, well, that is the same thing as log base b of 32, the first one, divided by 4. And of course, I can divide 32 by 4, getting 8, and this is our complete condensed form. So we went from this expanded form up here, all right, of this expression, and we simplified it down or condensed it down to log base b of 8. So these two are equivalent. All right, let's do another one here, and this one is going to be expanding now. So now we're going to start with the condensed form. We're going to apply our properties to expand this out as much as possible. Okay, so I have log, and it doesn't have a base here. So if the base is not listed, then it is the common log, which is a base of 10. But we don't actually have to write that down. It's just something to note in our heads. But anyway, so I have log of 9 times x to the 5th power. And so what I'm going to do first is, now number one, this to the 5th power is not applied to both of these. If this was 9 to the 5th power and x to the 5th power, that would be 9x all to the 5th power. Then I could actually move that out front, but that's not the case here. The 5th power, the exponent of 5, it only pairs with the x, so I can't actually move that out front yet. So what I'm going to look at first is splitting these up. Really, this is 9 times x to the 5th power, which means I can apply our product rule and split it up or expand it by addition. So that's the same as log of 9 plus log of x to the 5th power. And now that I have this more simplified version of just x to the 5th power, I should be able to move that 5 out front and getting my final expanded form of log of 9 plus 5 times log of x. And that is it. That's as far as we can go. Now, some people might say, like, well, you could go further. Log of 9 is actually log of 3 squared, so that could be 2 times the log of 3. No, you're not expected to do anything like that, okay? So, once these... you don't have to break down numbers into their factors, essentially, to keep on expanding out. All right, let's do one more problem. This one's going to be a little bit harder because we're going to have essentially fractional exponents. Okay, so let's go ahead and check this out. So we're going to expand log of the cubed root of y, which, by the way, the cubed root is the same thing as y to the 1/3 power. So it's really important to know how to transform a radical into a fractional exponent. So I'm going to repeat that. So the cubed root of y is the same thing as y to the 1/3 power. Okay, so we'll apply that later on. But anyways, ultimately what I have here is something divided by something else. So what we're going to do first is we're going to apply our quotient rule and expand that by taking the numerator and then subtracting off the denominator and separating these logs. Oh, by the way, this is log base 10 since it's not listed for the base. But anyways, so we went ahead and did that. So that's log of, and you can see I converted this, y to the 1/3 power, right? This is the same thing as the cubed root of y. But anyways, so y to the 1/3 power times x to the third, and then minus log of the denominator, which is z. Now I'm noticing that I can apply the product rule to expand this one right here. I have y to the 1/3 times x to the third. And so let's go ahead and apply that. And so we can split this up, this first term, to log of y to the 1/3 power plus log of x to the third power. And then, of course, we still have our minus log z. And then finally, we can take our exponents and we can move all of those out front using our power rule here. And so the 1/3 goes out front. So we end up finally with 1/3 times the log of y for that first term plus 3 times the log of x minus the log of z. Okay, and so those are all of our examples. And you might be wondering, like, why am I doing this? Why are we practicing these properties of expanding and condensing? Because it really is just practice. And the answer to that is pretty soon we're going to start solving logarithmic and exponential equations. And you have to have a really good handle on how to apply these properties in order to properly attack those types of problems. Okay. All right, guys. So there's our lesson on the properties of logarithms. Hopefully I made it nice and simple for you. And yeah, I hope to see you in the next one. Bye now.